Hi, welcome to our new video MCQ set 1 of diodes. Question: the depletion region is created due to option A, thermal generation of carriers, option B, movement of majority carriers across the junction, option C, movement of minority carriers only, option D, light falling on the junction. For getting the answer, first we can discuss what is a PN junction, how a PN junction diode is formed. A PN junction is formed when an N-type material and a P-type material are fused together. It will create a semiconductor diode. When a P-type and an N-type material are joined, the electrons from the N region will diffuse into the P region and the holes from the P region will diffuse into the N region. This occurs due to the concentration gradient. That is, this movement will be from the higher concentration to the lower concentration. As the electrons move from the N region to the P region, they will combine with the holes in the P region. And similarly, when the holes move from the P region to the N region, they will combine with the electrons in the N region. After combination, the junction near the interface is left with the fixed ions. You can see the fixed ions here. And the negative ions will be in the P region and the positive ions will be in the near the N region. These ions cannot move, creating a region which is depleted of free charge carriers. That is, this region is known as the depletion region. This is depleted of charge carriers. That's the reason why it is known as depletion region. It is known as depletion region. Okay. The fixed ions will create an electric field which is pointing from the N region to the P region. This will oppose the further diffusion of electrons and holes. The junction reaches an equilibrium when the diffusion current will be equal to the drift current, and the potential difference which is across this depletion region is known as the built-in potential. Okay, sometimes it is called a built-in potential or barrier potential. Okay, for the case of silicon, it is 0.7 and for the case of germanium, it is 0.3. So, the answer for this question 1 is the depletion region is created due to the movement of majority carriers across the junction. The majority carriers will diffuse across the junction due to the concentration gradient, leaving the leave behind the ions, which forms the depletion region. So, the answer is option B. Next question. The immobile ions in the depletion region are option A, free electrons, option B, free holes, option C, fixed donor and acceptor ions, option D, photo-generated carriers. We had seen that in the depletion region, there are fixed donor and acceptor ions. Okay. When the electrons and holes leave their positions, the ionized donor and acceptor ions will be remaining there and it will be forming the immobile ions. Okay, this is known as the fixed and acceptor ions, the immobile ions in the depletion region. Next question. The built-in potential of a PN junction is developed due to option A, external supply, option B, barrier created by the immobile ions, option C, heating of the junction, option D, recombination only. We know that the built-in potential of a PN junction is developed due to the barrier which is created by the immobile ions. Next question. The depletion region width depends primarily on option A, doping concentration, option B, crystal orientation, option C, lattice constant, option D, temperature only. We know that the depletion layer width, it mainly depends upon the doping concentration. If the doping concentration is high, width will be narrower. Okay. And if the doping concentration is low, width will be wide. Okay. So, the depletion region width depends primarily on the doping concentration. Next question. The diffusion current in a PN junction is caused by option A, electric field, option B, concentration gradient, option C, thermal gradient, option D, external voltage. We had discussed the diffusion current in a PN junction is caused by option B, the concentration gradient. Diffusion current arises because the carriers will move from the higher concentration to the lower concentration region. That is, the diffusion current in a PN junction is mainly caused by the concentration gradient. Next question. The drift current in a PN junction is due to option A, thermal generation, option B, electric field in depletion region, option C, the recombination, option D, diffusion only. The drift current in a PN junction is created by the electric field which is created by the immobile ions. It will push the charge carriers which will produce the drift current. So, the drift current in a PN junction is mainly due to the electric field in the depletion region. Next question. The built-in potential is also known as option A, breakdown potential, option B, contact potential, option C, threshold voltage, option D, saturation voltage. The built-in potential is also known as option B, contact potential. Next question. A PN junction diode conducts heavily when it is option A, reverse biased, option B, forward biased, option C, unbiased, option D, both. Answer. We can just discuss what is forward bias, what is reverse bias. We can see that this is a figure of a forward biased PN junction diode. We can see that the P side of the diode is connected to the positive side of the battery and the N side of the PN junction is connected to the negative side of the battery. And also we can see that when the diode is in the forward biased condition, the depletion region width, it will decrease and also the barrier potential will be lowered. When it is forward biased, more current will be flowing as the more charge carriers will be diffusing through the junction and the recombination happens. And the magnitude of the forward current will be in the range of milliampere range. Now, here the depletion region width, you can see it will be narrower and the barrier potential will also be lowered. Now we can move on to the reverse bias. In the case of reverse biased PN junction, you can see that the P-type material, it is connected to the negative terminal of the battery and the N-type region is connected to the positive terminal of the battery. Okay, here the depletion region width will be increased and also the barrier potential will be increased. And also here very less number of charge carriers will be crossing the junction and recombination will be happening very less. So, there will be the magnitude of the reverse current will be extremely very small and it will be in the order of microampere range or less. So, this is the forward biased condition and this is the reverse biased condition. During the forward biased condition, the diode will be heavily there will be heavy flow of current, and the reverse biased condition, the conduction will be very. So, the PN junction diode conducts heavily when it is, we discussed, when it is forward biased. In the forward biased condition, it will reduce the barrier potential and also it will allow majority carriers to flow easily through the junction. Next question. In a silicon diode, the typical forward voltage drop is approximately option A 0.1 volt, option B 0.3 volt, option C 0.7 volt, option D 1.1 volt. In the case of silicon, the typical forward voltage drop is 0.7 volt. Next question. In the reverse bias, the width of the depletion region, option A decreases, option B increases, option C remains constant, option D becomes 0. We had seen that in the reverse biased condition, the width of the potential barrier will increase. The answer is option B. Next, the current flowing under reverse bias is mainly due to option A majority carriers, option B minority carriers, option C recombination, option D the whole injection. We know that the current which is flowing under the reverse bias condition is mainly due to the minority charge carriers. The reverse bias current will be very less, only some minority carriers will be crossing the junction. The majority carriers will be pushed away from the junction by the external battery potential. Now, next question. Reverse saturation current I0 in a diode. Option A decrease with temperature, option B increase with temperature, option C remains constant, option D depends only on the applied voltage. The answer is option B, it increases with the temperature. The reverse saturation current increases with the temperature because more carriers are thermally generated. So the answer is the reverse saturation current I0 of a diode will increase with the temperature. In reverse bias, the diode ideally behaves like option A short circuit, option B open circuit, option C a resistor. Option D, a capacitor. In reverse bias, an ideal diode will behave as an open circuit. The answer is option B. Next question. The reverse bias current in a diode is typically in option A, amperes, option B, tens of amperes, option C, milliamperes, option D, microampere or nanoampere. The reverse bias current in a diode is very small. It is in the microampere range. Next question. The reverse saturation current of a PN junction varies approximately as. Option A, I0 is proportional to e raised to minus V. Option B, I0 is proportional to T. Option C, I0 is proportional to T square into e raised to minus Eg by Kt. Option D, I0 is proportional to 1 by T. The reverse saturation current in a PN junction varies approximately as I0 is proportional to T square into e raised to minus Eg by Kt. That is, the reverse saturation current depends upon the temperature and also the band gap of the semiconductor material. So, I0 is proportional to T square into e raised to minus Eg by Kt. Next question. In a reverse bias, the breakdown occurs when? Option A, drift current becomes 0. Option B, electric field exceeds the critical field causing ionization. Option C, the diffusion current becomes dominant. Option D, drift current and the diffusion current becomes equal. In the reverse bias, the breakdown occurs when the electric field will exceed the critical field causing ionization. Question. In the diode equation, I equal to I0 into e raised to V divided by eta Vt minus 1. The term eta is option A, temperature coefficient, option B, ideality factor, option C, reverse saturation current, option D, thermal voltage. You can see the diode equation of a PN junction diode is known as what? The Shockley's diode equation. This is the Shockley's diode equation is I is equal to Is into e raised to V divided by eta Vt minus 1, where I is the diode current, Is is the reverse saturation current, which is typically in the range of minus 12 to minus 9 ampere, and V is the voltage across the diode, and Vt is known as the thermal voltage. Then Vt, we know that Vt is equal to Kt by Q. After substituting the values, we will get this is equal to 26 millivolt. So, Vt is the thermal voltage and eta is known as the ideality. This here it is represented as in N or it can be represented as eta. This is ideality factor. So, this is the diode equation. I is equal to Is into e raised to V divided by eta Vt minus 1. Vt, the value is 26 millivolt. Okay. So, the diode equation I equal to I0 into e raised to V divided by eta Vt minus 1. Eta represents option B, that is the ideality factor. Next question. The thermal voltage Vt at a room temperature is approximately option A 26 millivolt, option B 0.7 volt, option C 1 volt, option D 0.3 volt. We know that Vt is equal to Kt by Q, that is equal to 26 millivolt. So, the answer is option A, that is 26 millivolt. Next question. In the forward bias diode, the IV characteristics, the current, option A increases linearly with voltage, option B increases exponentially with voltage, option C remains constant, option D decreases with the voltage. This is the IV characteristics of the diode. This represents the forward characteristics and this is the reverse characteristic. Thus, we can see that the characteristic plotted versus forward voltage versus forward current, then reverse voltage versus reverse current. In the forward bias, when the diode is forward biased, the barrier potential will decrease and it will allow the current to flow. For a small applied voltage, the voltage will be very small, and when the applied voltage exceeds the threshold voltage, then the current will increase rapidly. Okay. this knee voltage or the cut-in voltage is 0.7 in the case of silicon, and it is 0.3 in the case of germanium. Now in the reverse bias region, we can see that when the diode is in reverse bias, we know that the reverse bias potential will increase, and also a very small leakage current will be flowing when the reverse until the reverse voltage becomes equal to the reverse breakover voltage. Once the reverse bias becomes higher than the reverse breakover voltage, there will be a breakdown, and then the diode will conduct heavily. You can see that. Okay, until this is known as the leakage current, and it will be very small. Okay, so in the forward bias diode, the IV characteristic, the current will increase exponentially with the voltage. Next question, the slope of IV curve in the forward bias represents. Option A, dynamic resistance. Option B, static resistance. Option C, breakdown voltage. Option D, reverse saturation current. We know that the slope of an IV curve, it actually represents the dynamic resistance, that is dV by di. Okay, that represents the dynamic resistance. Now next question, the diode dynamic resistance RD is given by what? RD is equal to V by I. Option B, RD is equal to dV by di. Option C, RD is equal to I into dV by di. Option D, RD is equal to V into dV by di. We know that the slope or the dynamic resistance RD is equal to dV divided by di. In reverse bias, the diode current is nearly constant because option A, majority carriers dominate. Option B, minority carriers dominate. Option C, diode behaves like a short circuit. Option D, voltage is 0. In the case of a reverse bias diode, the current is mainly due to the minority charge carriers. So the answer is option B. Next question, the junction capacitance of a diode is in reverse bias. Option A, increases with applied voltage. Option B, decreases with applied voltage. Option C, remains constant. Option D, becomes infinity. We know that the junction capacitance Cj is proportional to 1 by root of Vb plus Vbi. So we can see that as the junction capacitance is inversely related to the reverse bias voltage. So when the junction capacitance of a diode in reverse bias decreases with the applied voltage. So the answer is option B. Next question, the diffusion capacitance in a forward bias diode. Option A is negligible. Option B, arises due to the storage of minority carriers. Option C, exists only in reverse bias. Option D is independent of forward current. The diffusion capacitance. The diffusion capacitance in a forward bias diode is mainly due to the storage of minority charge carriers, and it is proportional to the forward current. Okay, so the answer is option B. Next question, in a PN junction, the saturation current I0 increases with the temperature because option A, barrier potential decreases and more carriers are generated. Option B, diffusion coefficient decreases. Option C, majority carriers disappears. Option D, applied voltage increases. In a PN junction diode, the saturation current I0 increases with the temperature because option A, the barrier potential decreases and more carriers are generated due to the thermally generated charge carriers as the temperature increases. So the answer is option A. Thank you for watching. Please do